since I don't know. Or more like 10,000 times more than the luminosity of a normal galaxy, so they are way much brighter than normal galaxies. And for the variability, like the variability of the AGN is very high, especially for the X-rays. And well, for example, like our Milky Way is a normal galaxy, or Andromeda is a normal galaxies. And for AGN, we have, for example, NGC 7314, which is our study case in the end. Well, this is two images of a normal galaxy or spiral galaxy M100 and an AGN, NGC 7742. Well, as we see here, like from first glance, we think that it might be so easy to distinguish between a normal galaxy and an active galaxy. But back to 1909, Fat, when he first got a spectrum of NGC 1068, he thought it was a nebula at first. He didn't like from the first one, but at 1926, Hubble came with got like a better spectra of the same galaxy and other galaxies, which are 4051 and 4151, and it was the first time where we distinguished between between a nebula and AGN, and that was our first time to know that this new type of galaxies. Well, after that, there was a multiple contribution from many scientists, starting from Seifert, 1943, in which he discovered this new type of galaxy, Seifert. But at first, he thought it was a phase that every galaxy passes by. Well, I'm gonna discuss this later. A new different type of galaxies from the ones that we know. And the other scientists, MC Hardy, Elvis, Ward, they all contributed with their researches about the AGN, and they discovered that like from 5 to 40% from the emissions of like from the bolometric luminosity of the AGN is as a form of X-rays. And that's why it's really necessary to study AGN using X-rays, because like it represents like 40% of the emissions from it. Well, after that comes Keyes and Messrs, in which they proposed a model that suggested that AGN is empowered by an accretion disk, and all the emissions are that we receive are from the accretion disk, and it was supported by an indirect evidence of the existence of supermassive black hole in our Milky Way. And this one was proved like a few years ago by getting the first image of the black hole in our Milky Way. Well, after that, we're gonna move to the morphology of an AGN. Well, as we see here, there is a supermassive black hole in the center of the galaxy, and this supermassive black hole is orbiting all the matter around it, like making it in the form of a disk, which is called the accretion disk. And we have also the gases that are surrounding the black hole. They are very hot gases, which is also called the corona. And these gases, like there is the first one, the borderline region, which are very hot gases and also orbit in the black hole at very high speed. And there is the narrow line region, which are like relatively lower, have a lower temperature than the closer gases, and they also have a lower speed than the other ones. And at the end, we also have like a dusty torus, or a dust that is surrounding the entire system. And well, there's also the jet, but we're going to talk about that much. And moving to the other side, the radio-quiet quasars, Seyfert-1, Seyfert-2, those are the types of the AGNs. And this is also called the unified model. And the unified model describes that all these types of galaxies, like radio-quiet quasars, Seyfert galaxies, quasars, and blastars, they are all the same celestial objects, but it all depends on the angle we are observing these galaxies from. Like, for example, the Seyfert-1, there are galaxies in which if we got like the X-ray spectra of Seyfert-1, we're gonna observe both the broad lines and the narrow lines. But for example, if you are observing a Seyfert-2 galaxy, we're only gonna get like the broad lines, because I mean the narrow lines, because the broad lines are because there is the dusty torus, which will prevent us from observing the broad lines. And well, this is the unified model. Well, we're gonna move now to the next slide, which is black holes and X-rays emissions. I mean, black holes are supposed to be black. Like, where do we get the emissions from, the X-rays from? Well, to answer this question, we need to talk about the accretion disk, or the accretion disk of the AGN. So why does the informal matter from a disk around the black hole? Well, the short answer is the conservation of the angular momentum. But that doesn't make a lot of sense, so we have to move to the long answer. Well, the long answer is the material in the galaxy orbits the center, which is the black hole. And the closer the material from the black hole, the higher the speed it has. Well, but the problem is that the matter is orbiting the black hole on different planes, as we see here. Like, they are not all orbiting the black hole on the same plane. And as they are orbiting the black hole, there will be a collision between different particles from different planes. And because of the conservation of the angular momentum, as two particles collide, there will be, like, in the end, like, the vertical and the horizontal components of the velocity will get the mean value of the components of the horizontal and the vertical ones. Well, when we talk about the horizontal components, we are talking about the direction of the orbitation around the black hole. Like, at the end, all the matter will be orbiting the black hole in this on one direction, on the same direction, which is the direction of the majority of the particles. But when we talk about the vertical components, two particles of different vertical components collide. In the end, we're gonna get like the mean value of the vertical component, and that will lead us to something like this, which is a disk that all the matter surrounded black hole all in one direction. But the problem is that, as we see here, the second point, like, this matter are surrounding the black hole with different speeds. And as we have different speeds over different layers of the black hole, it means that there is a friction between the different layers. And this friction between different layers will lead to the increments of temperature, and also will lead to the different radiations, like from the radio infrared to infrared, visible UV, and until the X-rays. And my study will focus on the X-rays. Well, now we're going to talk about the different mechanisms that leads to the X-rays emissions. Well, the first one is the inverse quantum scattering, which is, as known, like the electron will absorb a photon and then it will emit an X-ray. And the second one are the emission lines from the different atoms, or the different materials that exist in the accretion disk. As different materials absorb the radiations, they will lead to as electrons from different shells absorb the radiation, they will move to the next level, and as they go back to the original level, they will emit a radiation, which is in form of X-rays radiation. Well, this is the main two mechanisms that will lead to the X-ray spectrums. Well, now this is the form of the X-rays spectrum of an AGN. as we see here, there's the primary continuum, which is coming from the corona mainly. And we got this from the inverse quantum scattering, which is very strong. And we can see also the iron line. And the iron line is mainly receive the iron line from the reflection of the inverse quantum scattering on the accretion disk. Well, my work is from 2 kilo electron volt, sorry, 2 kilo electron volt to 10 kilo electron volt, which is the range of XMM Newton telescope. So as we see here, like the primary continuum is also called the power law, and here's the iron line. And as we see here, like there's different materials on the accretion disk, but the problem is that all these emissions from the other materials are very low compared to the power law. That's why it's impossible to observe them. And the only material that can be observed is the iron line, which is at 6.4 kilo electron volts. And yeah, well, as I mentioned before, the power law, we got the power law from the inverse quantum scattering, while the iron line is from the movement, from the atoms, the emission lines from our atoms. Now we have a study case of NGC 7314, which is a C-first galaxy with a redshift 0.0048 and the mass which is 1.7 million times the mass of the Sun. Well, it was observed numerous times previously with multiple telescopes, and there was also this, which is like the previous studies identified that there is a heavy absorption soft X-rays below 3 Kelvin, in which in my study I want to include this part, like I will take only the parts from 3 Kelvin to 10, 3 kilo electron volt to 10 kilo electron volt. Well, in this study we're going to use ICAY, which is software mainly used on Linux. And it is software that we use for fitting the data from the X-rays data from telescopes. It's already include the multiple models, like the physical models, for example, the power law or the absorption from the materials, and also the emission lines. And the platform we're going to use is ICAY Server. ICAY Server is an online platform that we can use ICAY on, and also it has multiple other uses. For example, you can use it for codes or Python or many other uses. Well, here are the sites for ICAY. Well, okay. This is what the next way. This is the data. We're plotting the data on ICAY. This is what the data looks like. And well, applying the model. First of all, we start by applying the model, which is the power law. The power law to include the intrinsic inverse quantum scattering. And in here, we are trying to find the best parameters. Well, as we see here, there's this two functions that we are trying to find the best parameters to fit this data here. And we are, as we said, like we are using the power law. The power law will include the intrinsic inverse quantum scattering, and TBABs will include the absorption of the X-rays all along the way from the source until the observation. And by using ICAY, we found that the hydrogen density is 1.7 10 to the power 22 centimeters square, and the photon index, which is gamma, is 2 in here. But as we see here, as we added the inverse quantum scattering, there is this part on 6.4 in there, which is, we can see like something that is not fitted, that peak in there, and that peak which represents the iron line, the iron emission line. And in order to fit that part, we have to use a Gaussian, which is also a model that is included in ICAY. And well, this is its function. And by using ICAY, with fitting the data, we got that emission line. It's on 6.4, which is characteristic of the iron emission. So we know that this line is of that of the iron. But as we see, like there is also another two other peaks, which are still not fitted. So we used again. We included also 2 other Gaussians. Well, like the first Gaussian, we got that there is a peak at 6.68 electron volt, and a third one which is at 6.95. So what does this mean exactly? Like they are all an iron emission lines. Like the first one is the low ionized iron, or the neutral iron. The second one is the iron 25, and the third one is iron 26, which are ions of the iron, and they can only exist in in extreme conditions like that of around the black hole at a very high temperature and very high pressure. Well, the study wasn't really so accurate in the end, because we took an observation from 2001 and it was less accurate. Like if you look to another articles, for example, in this study from reference 6, in the study they took multiple observations and also a new observation, and they merged all these observations together with the low flux together and all the high flux together, and they got that there's not only the narrow lines, but there's also one of the lines is a board line, as mentioned in here. And yeah, so in order to get a better observation, we have to merge multiple. In order to get better parameters, better data, we have to merge multiple observations. And that was pretty much it. So after this, the next task is to include the relativistic effect models to determine the physical properties, like the height of the corona, the inner radius of the disk, the spin of the black hole, and the temperature. Well, thank you very much for your attention. If you have any questions, don't hesitate.
So yeah, if there is any question, I can go through you.
Thank you for a nice talk.
Thank you.
You mentioned the corona several times.
Yeah.
But this may be a stupid question, but will all of the material not get into the accretion disk? Will some like go further in but stay there as a corona, or how does the corona form?
Well, how does the corona form?
Because in the illustration it was further, or it was closer to the black hole than the accretion disk, and I suppose that the accretion disk like stops at the innermost stable circular orbit.
Yeah, exactly. Like the corona is closer to the black hole from the inner disk, from disk itself. So it's like the closest matter from the black hole itself. But I think it just takes time to get in the black hole. So, and during that time, it's got all those radiation because of the friction and temperature.
Any other questions? Okay, so thank you very much.
Okay, thank you very much for listening.
The next speaker is Karim from Mexico. So maybe yes, yeah, perfect. You have your laptop. So you're a PhD student, and you are also in cosmology, if I'm not wrong. Thank you.
Hi everyone. Thank you for coming. First of all, I would like to thank to the organizers for the opportunity of presenting this work. So I'm Karim. I am a PhD student in Mexico, and the title of this talk is Accelerated Constraints on dark scattering. So we will see where it starts. So a brief introduction for those who are not familiar with cosmology. So how do we discover the universe? The one ingredients of the cosmology is basically gravity theory, in this case general relativity. And well, the key assumption in cosmology is the cosmological principle, which stipulates that the universe is statistically isotropic and homogeneous in very large scales. With that principle, we can provide a solution to the Einstein field equations, which is the Fermi-Lemaitre-Robinson-Walker metric, which is there. And also we need to include what is within this universe. This is formulated by a perfect fluid, considering a energy tensor momentum. And then we can obtain, after many derivations, the well-known Friedmann equations, which is in the right side. The first one is the Friedmann equation, and the other is called the Ricciardi equation. If you can see, there are three variables: the A, which is the scale factor, rho, and the pressure. So in order to close this equation system, we propose an equation state, which is given by the abarotropic fluid. I don't know if you can see the cursor, yeah, which is this one. And also the scale factor is related to the redshift with this formula. And typically we assume the typical components assuming in the universe is given by these four components. With the first one is for matter in general, dark matter and baryons. The other one is radiation. For radiation, the third one is dark energy, and the last one for curvature. And with each has the value of the equation of state. However, present observations prefers the simplest model called the lambda CDM model, which contains basically 70% of dark energy. That is a thing that we don't know what it is, but it's accelerating the universe, accelerating the expansion of the universe. And the 25%, it's basically dark matter, enigmatic matter that we don't even know what it is, but it doesn't interact with the light, only pure gravity. And the 5% is everything that we know in physics. Well, we keep covering baryons. And so for Friedmann equation, basically, for a combination of these densities, you will obtain a solution given particularly universe. So there are some troubles on the lambda CDM, on the standard cosmological model. So we don't know what is this dark energy. Is this a simply constant, an exotic matter fluid, or some modification of the gravity that we don't know, or does it have interaction? So also there is another problem in cosmology, which is the data tensioning with some cosmological parameters. In particular, two of them. The one is H0, which encodes the rate expansion of the universe, the Hubble constant. It's a discrepancy between early measurements and late measurements. For example, supernovae, which is this one, SHUS, estimates a value of 74 plus minus 1.4, which is almost approximately 4.2 sigma tension respect to the early universe, which is in this case the cosmic micro-background measurements. Another tension on cosmology and another parameter, it's encoded in sigma 8, and typically in literature you will find it as S8. So for S8 we have this value on the early universe, while in late universe we obtain its estimated those values, for example, which is 2 or 2.5 sigma tension between them. So why is this happening? Possibly systematics that we don't know, or we are using the wrong cosmological model. So I would like to introduce my motivations. So we are currently in the next generation galaxy surveys. For example, Euclid, DESI, or LSST, or SKA. They will have improved statistical power, and there is a chance to solve this chance due to the greater precision in these new galaxy surveys. However, they will require a higher dimension parameter exploration, and that's what we need to accelerate those analyses for them. And another thing is the cosmological simulations have been a fundamental tool to study the global evolution of the structure, a very small case, but in the statistical context, it is not the most optimal thing to do because it requires a lot of computational time. I'm talking about months, maybe. And also, why we want to go beyond lambda CDM, as I mentioned, there are some discrepancies between some cosmological parameters. So there is a zoo in cosmology about alternative models, but in particular, I'm focused on an interacting energy model. That these models have shown to reduce such tension. I put here an example. It is the tension on lambda CDM, which and compared to early measurements. And for an interacting energy model, it's kind of diminished this tension. So that's why we are considered in particular a model. So the particular model that I'm working on, it's called the dark scattering. This model was inspired by Thomson scattering with electrons and photons. But in this case, it's like switching places. Dark matter plays the role of the electrons, and dark energy plays the role of photons. So as you can see, this is the formula basically from Thomson scattering. Since nothing provides us for allowing the dark electron to interact, we can just include this interaction manually. So this is how the equation of motion is modified. This is the interaction term that is included. And as we can see, we have this model that has the particularity that has a well-defined limit lambda CDM when the equation of state for the dark energy is set to -1, the interaction is vanished. So, and because one proof how do we prove cosmological models? One option is coming from weak lensing, a powerful tool, which is called the cosmic shear. Basically, the weak lensing refers to the statistical correct distortion in image that we observe. It is a sketch. Basically, this is what we typically see. And due to the lensing on the foreground, the model distribution. So this is encoded in this thing that we call shear. So the plan of on weak lensing is basically measure this correlation shear of two galaxies or the distribution of galaxies, given by this estimator. So I put here what is each thing, the tangential shear, cross-component shear, and also it's related with the ellipticity of these galaxies. So this is connected to the one important thing that we're going to see in a minute. It's called the matter power spectrum. So the cosmic shear is connected to this thing. So for instance, as I mentioned for the next survey, galaxy surveys generation, this is an example from Euclid, comparing to the current stage 3 photometric surveys. So as you can see, we expect higher accuracy on the measurements and more data. So that's why we need to model correctly the cosmic shear of the power spectrum. So, well, how will we model this model power spectrum in order to compute the cosmic shear? One option is called the halo model, which is inspired in n-body simulations. As I mentioned, the n-body simulations are our best way to study the evolution of the universe, but they are computationally very expensive. So one option is the halo model. It's basically modeling these nodes that it's highly nonlinear as a product of final outputs of n-body simulations. So you can see the evolution of the n-body simulation here, and this is how it ends. So basically, is obtaining the statistics of the correlation inside a halo and a difference correlation between galaxies in different halos. So this is how it's computed. I don't want to go in details here. So we can compute the nonlinear power spectrum of the matter using these formalisms. And other considerations with these formalisms are listed here. You can see this review from Curie for more details. But this is only valid for lambda CDM. We want to expand it to alternative theories, in this case, the dark scattering. Unfortunately, there is a formalism that is applied for beyond lambda CDM theories. It's called the halo model reaction. And here the reaction basically encodes every information of this modified theory, and is just included by this function called reaction in the matter power spectrum. This is already implemented in a code called React by Benjamin Bose. So basically, we modify this code to include this model, the dark scattering model, and this is the kind of the important things that we include. We modify the spherical collapse and the baryotron contributions. And then to validate our modeling, we compare to n-body simulations. So as you can see, here are 3 snaps at different redshifts. The dots are from n-body simulations, and the solid lines are the reactions. So as you can see, it's super% accuracy, a very small case. Just for those who are not familiar with, the k represents the inverse of the distance. So when I say small case, we refer to bigger case. So in this case, we are reaching super% accuracy at a very high nonlinear scales. So this is part of this paper, if you want to see. So how the dark scattering affects the matter power spectrum? This is, I put here a plot. We define the amplitude of the dark scattering as this formula. And well, it depends on the value of the equation state of the dark energy, so that's why it can be positive or negative. So this is how it is. Depending on the size, there is a suppression or an enhancement on the matter power spectrum. So this method is good, but it's not optimal yet for statistical purposes. So we are going to implement a code, called Cosmopower, which is a machine learning based code. Basically, this code is in Python and allows us to use data to train and create matter or temperature power spectra through use the neural networks that come from TensorFlow. So in this case, this is the architecture of the neural network. We pass some cosmological training parameters associated to the matter power spectrum, which comes from React. And this is why we use to train our target emulator. And in this case, our target emulator is the nonlinear power spectrum of the dark scattering. So basically, we produce 300,000 for training set and 10% for testing. And this is the range of each parameter where the emulator is valid. So in this case, we can see the emulator reach a super% accuracy also compared to React. So we emulate a good prediction. And also this emulator is capable to reproduce lambda CDM case by setting just the equation state to -1 and the interaction to 0. So that's good. And the difference in computation, for example, for React, generating 1,000 spectra takes approximately 8 hours, and with the emulator only 0.2 seconds. So it's very fast. It's a speed of factor of 10 to the 5 order. So now that we have a fast emulator, we want to use data to constrain the dark scattering model. In this case, we're going to use reclensing data for the survey kits, the calorie degree survey. We analyze the 4 data released from kits. It contains a galaxy cosmic shear that covers 1,000 degrees square. This survey measures 3 different statistical sets, but all these statistical sets are linear transformation from the cosmic shear, which is 1 powered, 2-point correlation function, and Clausewitz's. So before doing constraints on our model, we want to reproduce what is published. So in this case, with our emulator, we are able to recover what the official results from kits were produced in the lambda CDM scenario. So in this case, the standard pipeline from kits took like 5 days in 24 CPU cores, while using the emulator with the same settings. The only difference is the modeling of the matter power spectrum. It took just 1 hour. So now we can constrain our model. Now this is the priors that we that we consider in this work. Basically, are the same range of validity of our emulator. So this data is able to constrain the parameter of the dark scattering with this constraint, as you can see here. So also in the S8 omega plane, we confirmed that this interactive model, considering this work, it offers a promising alternative to solve just S8 tension. Also, you can see the paper here. As you can see, here is the dark scattering prediction and compared to the early universe. So conclusions, our prediction were validated. Our prediction from React were validated against embodied simulations. As you can see, we reached a 2% accuracy. We have developed an emulator using Cosmo Power that meets the precision required for stage 4 galaxy surveys, for example, Euclid. We optimized our statistical analysis by incorporating in the statistical pipeline, which is, I didn't mention, we use MontePython and estimate the parameters more efficiently. And employing kits data, we managed to constrain the dark scattering model. To do, we want to expand this analysis to different surveys, for example, DES year 3, or the recent joint analysis using kits and DES year 3. On the other hand, we can create synthetic data with features of the stage 4 galaxy surveys in order to interpret forecast or constrain this model. Wow. So I would like to use my acknowledgement and thanks to my collaborators. Well, that's it. Thanks.
Test.
Well, do we have any question? No? Okay, so now we'll just have a little break till, I would say, 10 past 12, no, 10 past 12 a.m. and then we'll go back here. The break is in the room right back. And after this, we will have a grand conference of Jean-Philippe Bizan about the current status of the lambda CDM model. Thanks.
Test. Ok, perfect. Test. C'est comment? Test. Tu peux couper le micro, la piste 1? Ok. Parce que sinon, on n'a pas de son sur le ligne en fait. Normalement, ils vont l'allumer. Ils sont prêts? Ouais, c'est bon. Ils nous font signe ou pas? Okay, so that is the third conference, great conference, and we have the honor to welcome Jean-Philippe Uzan, the patron with Hélène Courtois of ICAY 24. So thank you very much for coming. And what's an incredible presentation about theoretical physics and cosmology. We are really thrilled to have some new insight on the lambda CMD model, because that's what has been a common point between all the presentation in cosmology. What are the point of convergence and divergence on that? So thank you very much, and it's yours.
Yes, thank you very much. Can I get the slides, please? So hello to everybody. So I'm Jean-Philippe Uzan. So I'm a theoretical physicist, and I've been working mostly in cosmology and astrophysics, but my field is really theoretical physics. So I'm a specialist in general relativity, mostly, and field theory. What I want to do today, you know, cosmology is a huge field, and I'm sure that you have heard a lot of things about cosmology and, you know, all the tensions and problems the model had today. What I want to do is to try to explain to you on this particular example what is a model, the kind of question you can ask, when you should question physics and when you should question observations, and make a list about the problems we have today, and also try to explain to you why the way we do cosmology today is completely different to the way we were doing cosmology when I had your age. I was your age. So, non, il veut pas? Okay, so the main idea is that I'm sure you have all heard about dark matter and dark energy. I mean, at least in the press or by teachers, and you have read things. I mean, you are passionate about astronomy, so I'm sure you have heard about this. And what I will try to do is to start from the fact that we have this dark matter and dark energy. I will try to explain what are the hints that led us to think that we have this new kind of matter, and try to explain what are the hypotheses to make these deductions, because no one has seen a dark matter particle in the lab, so this is something which is completely elusive. We don't know what is dark matter, and I will try to tell you how we managed to get this kind of... C'est ma prise ou quoi? Aha. It works. Okay, it's easier for me. So I'll take this example, and then I'll come back on the standard cosmological models, and I'll try to highlight what are the hypotheses. When you use some theoretical physics laws or theories, you will always have to keep in mind that it is coming with a domain of validity and hypothesis. And if something is not working, you have to question yourself, am I in the correct domain of validity? Am I using the correct law for what I want to do? And if this is the case, what kind of hypothesis am I allowed to change? Because this is what will lead you to, I mean, when you do research, I mean, it's not like an exercise when you are at school. You don't have questions to solve. You have to find yourself the questions. And this is where you have to look to hypotheses, to things that everyone is taking for granted and it actually may be changed. And this is what I will give you some example of that. And then I'll come back on the need for this dark sector. And I will argue that cosmology is telling us today that we need new degrees of freedom, which mean either new kind of matter in the theories, but always maybe some more involved geometry for describing the space-time. And I will tell you, well, we know that, we have no idea what are these degrees of freedom, and I'll try to explain to you that we can make some university classes of the class of models that may be able to extend the lambda CDM. And that will lead us to see that we can design proper tests to test the hypothesis of the standard model. And this is also something which is important because I think it changes the way we think about cosmology today. So first, a short introduction to the standard cosmological model. Basically, what you want to do when you make a cosmological model is to start from some set of observations. So this is a map for the CFHTLS in Hawaii. But you have all the observations you can think of, the cosmic microwave backgrounds, all the observations that are made by astronomers. And from this set of observations, which are made at different epochs in the universe, with different objects, what you want to get is a mathematical and physical model of the universe. And you see there is a big step from going to here, because here it tells you nothing about space-time. If you don't know how light is propagating in the space-time, you don't know how to relate different images. And it's basically like, when you take a comic books, you have pictures, and your mind is actually filling the gaps between pictures, and this is your imagination and the consistency of the story which is doing that. And this is exactly what we do in cosmology. We have a lot of observation in different parts of the skies at different epochs, and we use the theory to tell a story, so basically to put all these pictures in a consistent way. And if we don't manage to do that, we may question, maybe one of these pictures is not correct. I mean, there are problems with observation, or the link we are using to thread them together as a problem, which means that we have to come back to the theory. The problem is that we are doing cosmology and we are talking about the universe. And I think when you do that, you always have to keep in mind that this is not doing science in the standard way of what people are telling, I am doing science. And the reason is that we just have one universe, at least. Some people imagine there are other universes, but we know we are living in one universe. This is our universe, and so we cannot test. The experience, the universe cannot be reproduced like you do in the lab, where you make many times the experiments and you see whether you have reproducibility. So we don't have reproducibility, and there may be some kind of difficulty to distinguish between fundamental laws and special initial conditions, and I will give you some examples about that. Then there is a historical dimension. What we have learned in 1 century is that the universe is changing with time, it's evolving, that the future is actually longer than the past, and it means that it changes the way we ask questions. Usually when you do mathematics or theoretical physics, you start from first principles and axioms that you state to be correct, and you use logics to deduce theorems. This is what we call deductions. It's not very useful to study the world because we don't know what the laws are and what are the correct hypotheses. What we do in physics is we do induction. We look at the world, we make experiments, we repeat them. When something is repeating always the same time, we say, waha, it should reveal some kind of laws of physics, and we try to make a mathematical formulation of this law of physics. And from this, maybe we are able to state a principle. And then if this principle is then stated as correct, we can deduce many laws, and we tested them against experiments. And as long as the experiments say you are correct, we think that this principle is correct. And maybe at some stage we will have to change our principle. So there is no truth like in mathematics where, what you have demonstrated will be always true. And in astrophysics and cosmology, we have to use another way, abductions. Because usually when you're doing physics, once you have the laws of evolution, you say, I prepare a system with some initial conditions, I let the system evolve in the lab, and I measure final situations. And basically, I compare the two situations, and I see whether they agree according to the fact that the system should evolve in a proper way. But for the cosmology, we don't know the initial conditions. So what we will do is that we will observe the universe. We will assume that the laws of physics that we have established in the solar system, in our galaxy, in our neighborhood are correct, and that we can use them to extrapolate in the past in order to reveal what were the initial conditions in the past. Okay, so you see it's very different, and so it means that there is a kind of extrapolation, and when you do extrapolation, the question you will always have to ask yourself is, are the laws that I'm using to extrapolate backward in the past, when the universe, on larger distance, higher energy, are they still holding true? And so, which means that you have to extrapolate, and you still have to control the domain, the validity of the laws that you are using to do that. So it means that we are not telling what is the universe, but basically what cosmologists are producing is scenarios, and we try to say among all the story describing the universe, what is the most probable scenario. And the most probable, which means that there are some kind of probability theory behind, which basically quantify our credence. The fact that I believe in this model more than this model. And there are many ways to measure that. And basically, it will come from the fact that, well, the theory I use to construct this model is a theory that I trust a lot in. If I say, okay, I use general relativity, there is no reason, no doubt today that we have a better theory of gravity, even though we can think about other theories of gravity. And then you will have the data, and the more data you get, this data can be, you are correct, or there is some mismatch. And at each time you have new theories or new observation, you can change the credence on your model. So this is something which is always updated almost year after years. And then you will look always at the consistency of the explanation. Also, you are all starting, your studies and research. I think this is something you have to keep in mind. You will find a lot of people who will try to explain dark matter by some weird phenomenon or say it doesn't exist. But then you will realize that you cannot just change the model in one part of the sector just to explain this, because it will have consequences in many observations. And as soon as you find an explanation that can explain, a theory that can explain many phenomena, then it will higher its credence. So this is why we have to be very careful when we say something about the universe, because most of the time, all the characteristics or the properties I will tell you about the universe, they depend on all this structure. When I say, and I'm sure you know about that the universe is 13.8 billion years, is it something true? It's not true as the fact that we are sure it will never change. What we want to say is that in this model, given the data we have, we can reconstruct what we call the age of the universe, and we have to give a precise definition of this term, age of the universe, and then we can estimate this age to be 13.8 billion years. Imagine that we replace cosmological constant by some kind of quintessence. We say general relativity does not hold in primordial universes or whatever. Maybe this age will change even if we just keep the same data. So it means that a lot of things we are saying about cosmology, they depend about all these hypotheses, and this is why we have to be sure that this model is correct, and we still have to test this model. So in the history of cosmology, we have mostly 4 eras. You see, I would say that cosmology is just barely 1 century old. It depends how you count. 1915, Einstein wrote general relativity. 1917, there is the first cosmological models made by Einstein himself about a static universe, and this is the first time someone is trying to guess out what is the geometry of the universe. He has almost no data, so basically it's a very theoretical model. It's a static universe because nothing indicates that the universe should not be static. So you don't change things just because you want to change them. Basically, he was just saying what we call today the galaxy. No one knew in 1917 that there were other galaxies. He sees the motion of the stars in our galaxy. he just assumes the universe should be finite, and this is mostly for mathematical reasons because the equations are easier to solve. He sees stars distributed in the sky. He doesn't know how stars are distributed. He supposes that the density of stars is the same in all parts of the universe. Finite universe, homogeneous matter distribution, static universe. And he realized that if you make these three hypotheses, you cannot solve the equation. You have to add this cosmological constant. And then this is basically the end. And then during the first years, it will be doing cosmology is basically doing some kind of mathematical exercise in general relativity, finding the mathematical solution to the Einstein equations. And in 1924, there is a paper by Alexander Friedman who says that he will take the same hypothesis as Einstein, but basically he will realize that the solution that Einstein found is a particular solution, that there are a lot of solutions, but they all describe a universe in which space is expanding with time. And as you may know, he tried to tell Einstein that he discovered that. Einstein saw that it was not correct, and it took about 2 years before Einstein realized that actually he made a mistake in his computations, and so that Friedman was true, but he saw that it cannot be. I mean, I don't think the universe should be this way, because probably he was, he was brought in a Newtonian era where space was absolute, and then at this step he stopped to do cosmology. And then for about 30 years, people were finding this solution, how is the universe expanding according to the matter it contains. There were almost no observations. 1924, this is the first time someone observed another galaxy in the universe. This is a famous observation by Edwin Hubble. So after that, it changes. We have galaxies. But you have to remember that it's less than 1 century. I mean, this Christmas, I think it was on the 30th of December 1924 that he told that the American astronomical community that he discovered a new galaxy. So this Christmas, New Year, it will be the 100th anniversary of the discovery of another galaxy. All of you have seen pictures of galaxies since you are babies. We have catalogs of galaxies with billions of galaxies. For sure, it changes the way we describe the universe. If you have 2 galaxies, how can you prove that the universe is expanding? And then in 1929, there is this famous observation about the fact that galaxies are drifting away from our galaxy, and this is the proof of the expansion of the universe. But basically, we don't do physics, we do mathematics. Then in the 40s, people realize that if the universe is expanding, if you go back in the past, the universe is denser, hotter, which means that if you take any composite object, take a molecule, you hit a molecule, it will break into atoms. You go back further back in the universe, it's hotter, the atom will be broken into protons and neutrons, and even the proton and neutron will be broken in quarks and so on. So all the things that do exist here were not existing a fraction of time after the Big Bang. No carbon atoms, no nitrogen, nothing. Which means that you are composed of carbon, oxygen, and so on. Where does this matter come from? And in 1931, Georges Lemaitre, which is supposed to be called the father of the Big Bang theory, stated that. He said, if we want to explain something, we even have to explain the atoms that compose us. And so where are the atoms coming from? And this is what started in the 40s. People realized that, okay, the universe is expanding and we have to do physics in an expanding universe. And it changes a lot of things. And so in the 40s, this is just the time where we were actually starting to understand nuclear physics. And people started to do nuclear physics in an expanding universe. And from that, they understood that there is something, and I will give you a flavor of that later on, that there is a way to explain how the first nuclei, deuterium, helium, lithium, starting to be synthesized about, let's say, between 2 and 20 minutes after the Big Bang. And for the other elements, that was understood mostly in the 50s and 60s, we understood that they were made during the evolution of stars. But you see, as soon as you realize that, it changes completely the way we think about the universe. And then we had to explain the fact that we had galaxies. Where are the galaxies coming from? This is what we call the large-scale structure. How are the galaxies distributed in the universe? Can we understand that? Is it consistent with the theory of gravity? Because we think that if we start with a matter which is almost homogeneous, there may be some fluctuation of densities. Are these small fluctuations of density able to grow, to make clumps of matter which are big enough to make galaxies and which are distributed among space in a way that we observe in catalogs of galaxies? And then in the 80s, we started to want to be closer to the Big Bang theory, and people realized that, but you have to mix general relativity with quantum physics. And this is where we're starting to talk about inflation and the primordial cosmology. But so you see, you have a series of eras historically, because you cannot do primordial cosmology before you did the other steps. And so you have all these layers, and each one is extending the previous, and they all rest on some observations. And at each step, it draws new questions, which means that the field of cosmology has evolved during 1 century. And if you are asking what is the Big Bang theory to someone in the 30s, in the 80s, or today, you wouldn't get the same answer. Okay, so this is to keep in mind that this is just a theory, and it tried to grow bigger and bigger and to answer more and more questions. And before we start, it's very important to realize that there are limitations. As I said, you have the Einstein equation. The Einstein equation, I didn't write the equation. Okay, it's okay. Did I? No, next slides. Okay. You want to solve the Einstein equations. So the Einstein equations are a set of equations that give you the geometry of space-time given the distribution of matter in the universe. They are completely correct equations, but there are 2 limitations. First, there is no way to solve this equation in a purely general way. So for those who have done some maths, this is basically a set of 10 differential equations which are coupled and nonlinear. There is no theorem in mathematics that will allow you to know whether you have a solution and whether this solution is unique, as you do usually when you solve differential equations. So there is no way a mathematician can tell you that there is a solution to these equations. And we know particular solutions, usually with some symmetries, and there is books of exploring all these solutions, but these symmetries, the universe has no symmetries, which means that we are not able, from a theoretical point of view, to get a solution which is exactly the one describing our universe. So basically, we will shift from the question of can we determine metrics that is describing the universe to the less ambitious question of can we determine metrics, there may be many, so space-time geometries, that are good approximation of our universe. And you see, when you make approximations, it means that you are doing physics. You are not doing maths anymore. But then there will be another limitation coming from physics, is that you want to go deeper and deeper with those observations, and you realize that if a galaxy ends further and further, it will be dimmer and dimmer, more difficult to measure. And these Einstein equations, they tell you that you need to know the matter distribution. So this is a light cone. We are supposed to be in the point O here. This is our world line. Time is flowing this direction. Here you have the trajectories of galaxies in space-time. And you see, for instance, this galaxy, when its world line is crossing our light cone, so light is propagating this way, we will observe these galaxies just when its world line is crossing our light cone. If a galaxy is here, well, I cannot observe it. So I will just observe a part of the universe, and then I will probably, if I go deeper and deeper in the past, I will miss observation. The dimmer object will not be observed. So I'm not able, from an astrophysical point of view, to actually measure the full distribution of matter in the universe. So I cannot solve the equation both from the fact that I have this mathematical limitation and physical limitation. And this is why we do these models, and we will start from symmetries, and this is what helps us to construct this model. But you have to keep that in mind. I mean, this is the basic before you start solving any equation. Okay, so if we want to do that, the program is, as I told you, fairly simple. You start from all this set of observations, you want a mathematical models, and you want to solve this beautiful equation. Okay, if you don't understand this equation, it's not a problem. I will not use it. It's just a picture, but this is the Einstein equation. And as I told you, no one knows how to solve this equation. And so basically what we will do, we will have 4 hypotheses. First, we will assume that there is a theory of gravity. This is general relativity. So basically that the metric the space-time geometries we will deal with are solution of this equation. Then we need to know what is the matter contained in the universe. We have learned from particle physics about during the last century that there is this standard model of particle physics, which is the classification of all particles in interaction that do exist today, so the quarks, the electrons, the muons, and so on, the neutrinos, and so on and so on. But this is not enough. One of the conclusions we have reached today is that if we want a consistent cosmological models, first we need this cold dark matter, we need a cosmological constant, we have no idea what this type of matter is. And then there is one more hypothesis I put here, is that what is the fluid hypothesis? I will give you an example of what it is. But you know, we are in this room, there is air, it's a fluid, it's a gas, but we know it's composed from molecules. Imagine the same thing. I take the matter in the universe on very large scales. I have galaxies. I can look at galaxies as molecules, or I can take big spaces and say, haha, this is a gas with an homogeneous density. How can I go from one to the other? In this room, it's very easy. I take a volume. I know there is the Avogadro number, which is huge. So I know there are a lot of molecules in this. And I can say, actually, if I take a volume, what is the fluctuation of the density from piece to piece. But I know there is this fluid approximation. Here, this is more tricky. Because you see, if I put the molecules here, and I want to go from molecules to density, I have to average this equation. I have to average it on the right-hand side. But the point is that this is a nonlinear differential equation, so basically averaging and solving the equation do not commute. So you cannot solve this equation saying, haha, this is a gas, and be sure that the solution you would get is a solution of this equation. This is what is called the back reaction problem. It's a completely open problem, and actually it's very difficult to formulate mathematically about what happens when you average a space-time. So I will give you some example of why we have to be careful about this hypothesis. Then, among all this space-time, we have to make some symmetry hypothesis to simplify the model, and we make what we call the Copernican principle. The Copernican principle states that we do not occupy a particular place in the universe. So basically, we are observing the universe from our galaxy. If we were in another galaxy at the other end of the universe, basically we will observe a universe which is barely similar to ours. Not identical, but similar to ours. And it's isotropic, which means also that if I observe the universe here and here and here in big patches, basically I should observe statistical properties which are identical in different directions. So it's a very, very important principle because all the model and the metrics we will be using rely on this hypothesis. And then there is an hypothesis which is less important at this level, which concerns the global shape of the universe. Because if I take a Euclidean plane, well, this is Euclidean geometry on an infinite plane, but I can make out of this a cylinder which has the same local geometry, but it will be finite around one direction, or a torus which will be completely finite. And the Einstein equations, they tell something about the local geometry, but not on the global topology. We know from mathematics that given a local geometry, there are a set of topologies that are consistent with this geometry, but we don't know whether how to determine it. So one of the questions could be, is the universe finite or infinite, and does it have a topology or not? Usually people assume there is no topology, but we can put constraints on that. So basically this is all what you have to keep in mind, and when you do this exercise, you end up with what we call the Friedmann-Lemaitre space-time solution, and there is just one thing that the geometry reduces to one function, which is the way the universe expands, the space expands with time. And this is what we call the scale factor. And here, so we call it scale factor, and it's A naught is the value today, and this is the way, and this is time, and this is the way the universe expands. And here are a set of solutions. I have two parameters here that I use, which is a relative quantity of dark matter and dark energy, or cosmological constant. If I take one point in this parameter space, it gives one type of universe. And for each type of universe, I can solve the equations and tell you how the universe expands. And what is interesting is you see there are solutions that start from what we call a Big Bang, so there is no space here. It expands and then it recollapses in a big crunch. You have some solutions that expand forever. You have solutions that don't go to a Big Bang, for instance. So which of these story of evolution of our universe is the one of our universe? Okay, this is a set of solutions, and to know that, we need to get data to distinguish between these different models. Okay, so this I think I've told you is that all these things are defined in a given model, and in particular the cosmological parameters, when we say that what we call omega, so the total amount of dark matter, which is a number between 0 and 1, when we say omega dark matter is 0.3, it means that there is, if I take the average of all the matter of the universe, 30% is dark matter. But these parameters, they are defined only in this framework. If you change the framework, then you will have to redefine all these quantities. Okay, so now let's come to this need for dark matter and other problems. So before to tell you many things about the universe, I want to tell you about the problems, because this is where we do research now. So the first is dark matter. Dark matter has a long story. It's not something we invented recently. The first hints of the existence of dark matter are from the 30s by Fritz Zwicky. And he was looking at what we call clusters, clusters of nebula. And basically, he was able to measure the velocities of this object and try to make a map of the distribution of mass. So basically, he can get the average value of the potential energy and kinetic energy. And from Newtonian, so we don't need general relativity to that. You put you take a gas of massive objects which are bound by their own gravity, and they move together. But the way they move and they do not escape means that they have a mean velocity that tells you how likely they have to escape. But the gravitational potential energy keeps them together, and there is a balance. And this can be encoded in a mathematical theorem that we call the virial theorem. And basically, if you are able to measure the dispersion of velocity and the total mass of the object, you can see whether this is consistent. And he was very puzzled by the fact that the galaxies, they move too much. I mean, the nebula, they were moving too fast. Given the estimation of the mass he had, the object shouldn't stay the same. The galaxy should escape. Okay, so here, if we are on Earth, we have atmosphere on the Earth. Why do we have atmosphere? The atmosphere has a temperature, the molecules, they have some speed, and they do not go to space because the gravity of the Earth keeps the atmosphere on the Earth. If the atmosphere was much hotter, then molecules may evaporate to the space. And this is exactly the same. No one believed him in the 30s. And then in the 70s, Vera Rubin, an astronomer, she was looking at a spiral galaxy, and she tried to measure the rotation velocity of stars in the galaxy. And so here you have the distance from the center of the galaxy. Here you have the velocity of the galaxy. And basically, if you think about a spiral galaxy, you have like the inner part, which is very bright, and I think most of the matter is in the center of the galaxy, and then you have arms, and then you see even stars where you don't see any, there are just a few stars. And basically what you were expecting is like in the solar system. Here you have a lot of matter, so the velocity, the rotation velocity should increase. But after the last part of the distribution of most of the stars, you should have a Keplerian decrease of the velocity. This is what we observe in the Earth. You have most of the mass in the sun. You have all the stars orbiting the sun, and the further you are, the slower the velocity of rotation. This is not what you observe. What you observe is these things. And it's as if the stars were reaching a constant velocity. And then she deduced that, well, to be true, it means there should be some matter to create a gravitational potential that allows for this velocity to go to a constant and not decrease. It could have been gas. She could not know at her time, but it was then shown that we can measure the gas in the galaxy. It's not enough. And basically, you need a halo of matter that you do not observe, that is not bright, which is what we call dark matter, around the galaxy. And this is what we call the dark matter halo of the galaxy. So this is a second observation, and you see, we detect dark matter here and here, from the dynamics of standard matter. We see bright objects, and in both cases, they seem to move too fast given the strength of the gravity. For the spiral galaxy, it's like being, you know, on comment on appelle ça? Okay, not on a swing, but I don't remember the word. But you know, if you are rotating, you know you have the centrifugal force, and you want the gravity which is pulling toward the center of the galaxy to balance the centrifugal force. And for these galaxies, they are going too fast and they should escape in space. This is not the case. Otherwise, galaxy would not exist. And then from there were a lot of observations, so it's not complete at all. Just to give you where we have been going from there, we can make lensing from galaxy clusters. So you see these big arcs and arclets. And you can map the distribution of matter, and then you see there is not enough matter. It's not distributed in a way that you get these lensing effects. You can see the collision of two galaxy clusters. This is the bullet clusters. You can map the gas with X-ray observations, which map the temperature of the baryonic matter. And then you see that lensing, which tells you a distribution of the total amount of matter, is offset with respect to the baryonic matter, the standard matter gas, which is in red here, and dark matter is in blue here. So basically, there should be this matter. You have the cosmic microwave background, which tells you that basically we also need dark matter, otherwise this effect of lensing on the cosmic microwave background will not be true, and this is something that has been obtained by the Planck satellite about 10 years ago. And now we can even make maps of the distribution of dark matter in our universe. So there are many hints that there is this matter on different scales. Scales of galaxy, scale of clusters of galaxy, scale of the universe. But we don't have any idea of where it's coming from. And actually, all these things were kind of known from the 70s when we started to do numerical simulation to understand the large-scale structures. And in the 80s, it was sure for many people that the standard cosmological models was a failure, in the sense that if you don't add a matter which is not known, the model doesn't work. And the reason is that here we have the observation from the CFA, Center for Astrophysics catalogs. Each point is a galaxy. And then we have this, so this is the way galaxy should be distributed. And then people started to make a numerical simulation with different kind of dark matter. And you see this is what we call hot dark matter, cold dark matter. And you see the morphology of these simulations, these two simulations, they really look like the way the galaxy were distributed. But these were with very few galaxies and computers of the 80s which were not very efficient. But since the 80s, it was almost sure that to explain the distribution of galaxies in our universe, we need dark matter. So to do that, to try to get a glimpse of what is this dark matter, we had two progresses. The first is concerned observation, and this is a list of the catalogs that we have today. Here you have the number of galaxies in the catalogs and the volume of the universe which is observed. And what you see is that you see in about 20 years, we got from 10 to the, let's say, 10 to the 4 to 10 to the 8th number of galaxies in the catalogs. So it means that we have so much galaxies in the catalog that we can start to make proper statistics. We can have good measurements of the distribution of the galaxy, also classification of the different kind of galaxies. So it has changed completely the field. It also means that you cannot deal with so much data without a computer. This is also, it explains why now you all read papers about AI techniques and deep learning and so on to deal with this data, because it's very difficult to do that without a computer. On the other hand, there was a big progress in numerical simulations. So here are the simulations. So this is the year of the simulations and the number of particles that you get, the mass of the smallest particles you get in your simulations. If you don't have a big computers, what you will do is that you will put very few mass with very few high masses, because you have to solve equation for the motion of each of them. And once the power of your computer increase, you put more and more smaller particles, which means that you gain in resolutions. So here you can just resolve in the 80s basically superclusters of galaxies, and today numerical simulation go to the scale of dwarf galaxies, which means that we can start to understand, yes, and now it's even better, because I didn't go follow, but they put the gas, and now we can understand the real distribution of galaxy, why different kind of galaxy forms, how many satellites does a galaxy have, what is the relation between the plane of the galaxy and the plane of orbits of the satellites, and so on and so on. All these questions we were completely unable to ask, let's say, 15 years ago. So you see the field have changed because we have these supercomputers, the fact that we can reproduce the universe in silico, and the fact that we have these massive observations. It doesn't mean that we shouldn't do theory, because theory also has made a lot of progresses. Okay, that I will skip. So we have this big problem with the dark matter. We have the problem also with the cosmological constant. Is coming from the observation since 1996 of distant supernova. And basically you see in this plane where you have the density of matter and the density of the dark energy, you see that you cannot have zero dark energy because of the CMB here and the supernova data. So basically we end in a model where you should have about 75% of dark energy and 25% of dark matter. So most of the matter in the universe is in an unknown form, which is not bright. It means that the matter that composes us is just a tiny part of what is in the universe, and this is very puzzling. Then there is another big problem. I told you that in the 40s, people start to understand that the light atoms were synthesized during the first minute after the Big Bang, and this is what we call Big Bang nucleosynthesis. The first paper was in 48. And basically, you say the universe, let's say 0.1 second after the Big Bang, was so hot that you just get neutrons and protons. And we know that these neutrons and protons, they can have nuclear reactions. The neutrons is not stable; it decays in protons, and then you can have a proton plus neutron give a deuterium, helium-3, hydrogen-3 or tritium, helium 3 and 4, beryllium, lithium-7. And we are able to compute all these things. If you put this nuclear reaction network on here you have the nuclear reaction. So for instance, it means that deuterium plus deuterium give tritium plus a proton. Each of them is a nuclear reaction. All these rates, nuclear rates, are measured in a very precise way in accelerators today. So we know all the physics. We put that in a computer, and what we get is the abundance of the different light elements, the helium-4, helium-3, deuterium, and lithium-7. The only parameter we don't know is how much photons we get for each baryon. You see, the more photons we have, the hotter the universe is, which means that the force, the photons, if you have a lot of photons with high energy, if you start to make a composite object, let's say deuterium, you will have energetic photons that will break the deuterium back in proton and neutron. So if the universe is too hot, you cannot get these light elements. The universe expands, and after a while, it's so dilute that the proton and the neutrons, they don't have any probability to meet to make deuterium. So there is a small windows, and this depends on the amount of radiation or light that we have for each baryon. And this is this number here. For a long time, we have no idea of what this number is, so we were computing the abundance in blue here, in function of this unknown parameter, the amount of radiation at the beginning of the universe. And you see, in green, you have the observation. So basically, it works well for helium. It works well for tritium, for deuterium. And here, we see that there was kind of a problem with lithium-7. Today, thanks to the WMAP and Planck satellites, we are able to measure this parameter. It has to be here. So this is coming from cosmic microwave background anisotropy. This is marvelous. You see, you have an observation with a tiny error bar here. You have this observation with a tiny error bar here, and these are the observations. Here, I make a zoom on it. It's very unlikely that you get like 2 observations and a theoretical prediction that fits so well. Okay, this is more than 0.1% accuracy. And then, if you believe that, you should be here. And actually, this is the lithium you get. So the universe should produce much more lithium than we have today. No one has a clue why. This is called the lithium problem. It has been there for 20 years. There were some ideas. I would say till 10 years ago, it was simpler because the error bar on deuterium was larger. It was going like that. So basically, you could find some models by, letting the fundamental constant vary or adding new particles that were solving these lithium problems. But now, because the error bar on deuterium has shrunk quite a lot, there is no way, we have no model, theoretical physics models that explain this. For the community, the main explanation would be that this measurement is not correct. It's very difficult to measure primordial lithium. You have to find the oldest star. You have to make some extrapolation to what we call zero metallicity. So basically to find the stars that you would consider as primordial stars. And it's very difficult to do. So there are a lot of people who say, haha, maybe the problem is not with the theory because it's working so well here. It's with the observation of lithium. But we don't have a proof of that for now. And then the last problem that is starting to point yes, about 10 years ago now, is about the measurement of the Hubble constant. So actually the expansion rate of the universe today. So here I put the plots of the measurement of the Hubble constant. This is time, and this is the value of the Hubble constant. In the 20s, 30s, when Hubble was making his measurement, we have huge error bars, and it was kind of fine. I say kind of because when you take this high value of the Hubble constant, for instance, you would get a universe that is too young. I mean, the universe cannot be, I think the age of the universe was like 3 billion years or something like that. And we knew there were objects older than that in our own universe. So it was kind of problematic. And then with increase of accuracy of observation, it reached to this value, and people were really happy in the 90s when I was doing my PhD and so on. This was not an issue. Actually, everything was going to the same constant here. But then we hired the accuracy of measurements, and we were able to measure the Hubble constant from different techniques. In the local universe, using the Hubble diagram from supernovas and weak lensing, this is the top here, and this is coming from the observation of the cosmic microwave background. And you see, in around 2000, the error bars were large, and everything was consistent. And then you make progress in the way you observe, you get smaller and smaller error bars, and actually, you don't have consistency anymore. So, this is a lesson. Things can work when you have large error bars, you make progress in the way you make your measurements, and it doesn't work anymore. And actually, this is what is going to happen for most of the things we have, because we have a model which is a simple model, and when you go to higher precision, maybe our theoretical predictions are not good enough. And today, we are working on trying to explain that. So is it a problem with the way we understand supernovas? This is a problem with the way we model CMB and we measure the Hubble constant from CMB, cosmic microwave background measurements? Or is it a problem saying that maybe we have a new kind of matter in the universe? So we don't know. We have clues, but we don't know. And here there is a last problem, which is called the SA tension. Basically, this is the way matter is clustering. I will not go into detail. It's too complicated I don't have time to tell you that. But just to say, there is also a problem. The amplitude of the fluctuations that are leading to galaxies are not consistent with different set of observations. So it's kind of weird, because we have a model which is working very well to explain a lot of things. And because we make a lot of progresses in measurements, we end up with a lot of tensions, but we don't have an alternative model to say what is the other way to do. So we have this dark matter, dark energy, and what is important to keep in mind is each time you will find an inconsistency, you always have 4 possibilities to resolve it. Either this is astrophysical, in the way that the interpretation of the data has to be questioned. For instance, the way you model your supernova is not correct, so it will make a bias in the way you construct your data set. Then there could be an observer bias, the fact that actually what we predict with the model is not the exact observation, it's a distribution of observation. We make some kind of average, because as I told you, I could be in another galaxy, there will be fluctuations. And actually, you can compute, if you make simulation, you can say, haha, one observer out of 10,000 should see this kind of deviation. Because when you have a distribution, you always have outliers. This is standard, and you have to expect that. The problem is that you observe the universe from one single place. It's very difficult to know whether this is an observer bias, but you always have to keep that in mind. It could be cosmological, which means that the way you extrapolate physics to and physical laws have to be questioned. These things about averaging is still holding? Is the Copernican principle correct? And then if this is not the case, you see, here I don't change the physics. I question the observations. I question my position in the universe. I question the hypothesis to construct the cosmological models. I don't change physics. And then in the end, if I have no solution, I have to change physics. So maybe I have new matters. I can change general relativities. And whatever I do for here and here, I have to introduce what we call new degrees of freedom, so new quantities to be included in the model, which are either geometrical to have more complicated space-time with the same physics, or to have new physics. And this is where we stand today, and for each of the problems, you have to go through this kind of questioning. So I will give you some flavor about the geometrical degrees of freedom, and how can we test the Copernican principle? When I was your age, in all books, it was written that the cosmological principle and Copernican principle was not physical, that it was like people were saying even philosophical. And the reason was that they were saying, you cannot test it. You observe the universe for one position, which is here and today. There is no way you can go to another galaxy to test. How come is it possible? Okay. And I was puzzled by that since my PhD, and actually I found a way in 2008. And the reason is the following, is that we are here, and as I told you, this is a light cone, past light cone, so the light is flowing this direction here, like that, and we observe here, and we see different galaxies, but it's not true that we observe the universe from one single position, because time is flowing. It's changing. Our position is changing in time of 1 second every second, which means that I observe the universe from here, but let's say in 10 years, I will be a little bit further away, and my light cone will not be this one, it will be another one. And this has deep consequences. Let me show you. I will spare you the maths. So this is my light cone today. This is my light cone today and a light cone in 10 years. And you see, I was observing a galaxy with a redshift of Z, and because I observe a little bit later, the galaxy has moved, and I should observe a change in its redshift. This is known from the 60s. It was done by Alan Sandage and Rob McVitie, and they were saying that they can compute the change of the redshift with time, so it's called Z dot. The dot is a time derivative. It was given by H naught, which is a Hubble constant, 1 plus Z, minus the expansion rate at the time of emission, so H of Z. And you can put numbers. And actually, this is tiny. It's basically 10 to the minus 10 in 10 years in relative change. And they argue in the paper, this is nice. If we make observation of galaxies, we have good observation, and we have to wait 10 billion years before it changes from 1%. So it's safe to make observation, but still it is changing. And in 2008, we realized that actually if you take a space-time which is not homogeneous, but which has expansion rates in different directions which are changing, or basically if you are in a void, this formula has to be updated to that, and basically this is just the expansion rate along the line of sight, not the average expansion rate. For a Friedmann spacetime, these two things agree. And the point is that the change, about 20 years of this redshift, you see it's 10 to the minus 9. For many years, people thought that we would not be able to measure it. Today, we know we can measure that. And there is a project which is the EELT, European Extremely Large Telescope, that is now being built in Hawaii, and this is the error bar we should get. So you see, here I made just a pure exercise. I put numbers on this. This is a pure Friedmann spacetime, which is calibrated with all the other observation. And then I can predict what this observation is, and I can make, so these are not true observation, and these are simulation of the observation, assuming that we have a universe like the one we model today, homogeneous and isotropic. Now I say, okay, can I make a universe with no cosmological constant but a big void around us, which explain all the observation along our past light cone? okay, that I can tune. This is possible. It's a mathematical exercise. You can do it. And you ask yourself, okay, for this new observable which take data out of the light cone, what does it change? And you see that for all the other observations, the two models will be indistinguishable, but for this new observation, there will be a difference. So this new observation which take information, off the light cone is able to allow us to test this principle. And now we have at least 2 or 3 models, techniques to test this Copernican principle, which means that we can observe the universe from other places, even though we are stuck on the Earth, which is kind of neat. Then there is these things about, I told you, the fluid approximation. Don't read this. I will just make a picture. You will understand very, very nicely. As I told you, remember that we have galaxies. They are distributed like that. This is, I would say this is a true universe. And I model it with a universe in which matter is distributed like a fluid of constant density. Okay, so basically what I have done to go from here to here, I've taken the matter, I've taken big spaces, I've made the average, and basically this is what I get. When I compute the observations, in particular, if I take a supernova exploding and I want to know what is the observed magnitude of this supernova, to get what we call the luminosity distance, I have to solve the propagation of light from the supernova to us. In the real universe, the supernova, let's say, is here. Its light is going this way up to the observer. And you see, most of the time, it's propagating in vacuum. Okay, there is a vacuum, and there is matter in small clumps. If you take a supernova is exploding. Basically, it will take the size of the solar system when it explodes. So basically, if I think about a light beam, the cross-section will be like one astronomical units. So it's very small. So basically, these light bundles always propagate in vacuum. When I make my theoretical computation, I assume that actually it's not in vacuum. It's in a region where I have a constant density. And from a mathematical point of view, it changes everything. In this situation, and if you don't understand, just forget about this. Here we have a non-vanishing redshift tensor and here a vanishing vial. And here this is exactly the reverse situation. How come? Is it possible that this model of this situation is correct? Okay? And that I pointed out when I was writing my PhD, and actually I was completely freaked out when I do that because I said, and I asked someone George Ellis, who is a very famous cosmologist, and we discussed, and he told me, it's not, people have asked this question for many years. There was a paper by Barzeldovic, there was one by, I forgot, who got the Nobel Prize, but it's not important. But no one is able to understand that, and there is no way to solve it. And actually, it took me more than 20 years to get the answer. Because I wrote my PhD in '98, and you see we get the answer in 2018 with 2 of my students. And the idea was the following. We took a universe like this model, which is completely flat, and then we take bubbles and we put all the matter inside the mass. So here, this is basically the space-time around the black hole, and this is the cosmological space-time, and you can show that this is a pure solution on the Einstein equation, which is called the Swiss cheese because of all these holes in the cheese. And you can compute what happened here and here, and you can start to understand how much it's making differences. And here is what you get. Imagine that you make, so this is a fraction of all that you have. This is a purely Friedmann spacetime with no structure in it. This is what you would get if you analyze the supernova data. Now imagine that I put a lot of holes. I simulate a supernova catalogs and I analyze it in this way. What I would get is actually that instead of measuring this, I will measure that. So I will make an error about 5% in the way I measure the density of matter. Okay, this is not an example. Then from this, we were able to make a theory and say, for each observation, how precise this assumption is and how far it impacts what you measure on these parameters. But it's very complicated because you have to go to small scale structures that you do not know. Here, we knew it exactly. This was the first like toy model to make an example. But actually, you would start by making some random, and you will use statistical physics techniques actually to evaluate what is the effect on the observable. And that does not require any computer. You do that with your hands and a lot of mathematics. Then you have the physical degrees of freedom. How many years do you have to finish my talk? No, I'm kidding. 5 minutes, 10 minutes? 10? Okay. Okay. So now I will write some equations, because as I told you, I'm sorry about that, I'm a theoretical physicist. Tell me, how many of you have never seen the formulation, this kind of notations with an action and so on? 2, 3, 4, okay, okay. It's very important because there are two ways to write down the laws of physics, okay? If you use, when you learn Newton physics, for instance, you write equation of motion. So, for instance, you say mass times the acceleration equals the force that is acting on my particles. I have an equation, differential equation. I give initial conditions, and I solve for this equation, and I get a trajectory. Is this okay for you? Everyone? Okay. There is another way to write down the laws of mechanics, which is called analytical mechanics, that was written in the 18th century. It's basically to say, I will consider all the trajectories going from one point to the other. I imagine all the trajectories. And I will have a kind of what we call action, which is basically measuring, I would say, something like the length of the trajectory between these two objects. And I will try to minimize it. And the claim is that if you minimize this function, then the trajectory that minimize this function is the one that you would get by solving the Newton equation. This is what we call variational principle, and then it can be shown that this is the best way to write down the laws of physics. Instead of writing a set of equations, we just write down a functional, which is a function. So these things is depending on the geometry and the matter inside the theory. And if you take this whole set of equations and you say, what is the structure that minimizes this quantity, you will get the Einstein equations, and so on and so on. And this is the way you write particle physics. And the important way is, why do we like these things more today than writing the way Newton was writing, you know, time, mass for the acceleration equal force, is that this is the best way to go to quantum physics. And this is why today you will all learn, if you do some physics, you will all learn this kind of techniques, because this is what we call classical field theory, but there is a natural way to get quantum theories out of this. And this has been tested in laboratory, and this is the way all particle physics is done today. So I'll try to tell you that for the kind of general relativity, we have two parts. We have the contribution of gravitation. So R is the curvature of space, which depends on the local geometry, and lambda is the cosmological constant. And G is the Newton constant. And then you have to tell how are the matter fields, this is all the matter fields, the particles, how do they couple to the local metric? And we say that they are all coupled to the same metric. So this is basically the minimal way of formulating the gravity theory. And if you use this theory, you will get the Einstein equations. Then, okay, so if you want to do new physics, to introduce new physics, you will have to modify this functional. This is also, it's better than modifying the equations, because if you have a set of equations, you modify one equation, you are not sure that it will be consistent with modifying the other equations. If you write this, you know that all the equations of the theory will derive from the same quantity. So whatever the change you are doing here, you are sure that you will get a consistent set of equations. So this is basically, you are safe with this. And also you can try to see whether you will have, I would say, appearance of negative energies or problem in your theory. You can read their techniques to start from this formulation and to make these diagnostics. So this is the way we write physics today. Okay, so we want to explain this cosmological constant, and basically we can say, okay, I put this lambda here. You see, this is a pure constant. I have a pure constant, and that gives you the lambda in the Einstein equation. But I could say, okay, now this is not a constant. This is something that is changing with time, which is dynamical, and I will try to replace it by another kind of matter. So the simplest way to do is to add this new part in red here, which is a spin 0, so a scalar field. It has a kinetic term, it is a potential. And you see, if I do that, well, I will get from here the Einstein equation, but I will have a new kind of matter in my theory. Okay, so this is adding new matter, and probably you have heard the word like quintessence and so on. This is the way you do, and you have a lot of models because you will have a free function here, you have this field, but you will not have a new force. You will just have new matter, and it will change the way the universe is expanding. And then you have another way, say, I could also change general relativity, have another theory of gravity. And the simplest way to do that is to say, I keep this part here that I had got before with this scalar field here, but I will assume that the matter is not coupled to the same metric. The metric will be dynamical in the sense that there will be a conformal factor here. And that will say that if I take two massive particles, two masses, M1 and M2, in the standard model, I just have a force which is coming from the exchange of the spin 2, which we call the gravitons, and it will give you on small scales Newton laws or Einstein equations. But because you have this coupling to the scalar field, there will be what we call a fifth force, a new force, which will have a strength I call alpha here, which will modify the way you measure the attraction between two masses. So if I do that, I have a new degree of freedom, a scalar field, which will modify the way two massive particles attract themselves. So instead of having, if I take Newton's law and I say, okay, what is the force between these two masses? I will get an answer whether I'm here or whether I'm here. Good. If I have this scalar field, it will change in space-time. So the action of the force here and here will not be the same because there will be this extra force that will depend on the position where you are in the universe. Okay, so this is a technique to make theories of gravity which are beyond general relativity. This is the simplest one. It's called a scalar tensor theories. Today there are like dozens of theories which are constructing in this way, and we try to classify them in a mathematical way. And basically, what was it? 2000 something, 2005, 8, 4. It was 2004. So we can try to say, okay, we have ordinary matter and we have the metric tensor. So if we just have that, we have general relativity. If I take a new kind of matter which is not interacting directly with matter, I get extra matter. If I have a new interaction, then I will have a deviation from general relativity, and then I add other mathematical possibilities. And for each of them, there are tests that you can make to distinguish between the models. So something now like that has been done in many ways now, and we have like a kind of map of all the ways not all, but a large number of ways to modify general relativity or to add matter in the model. And once we know that, we know which kind of observation we can make to distinguish between this model and this model. And in particular, we can test for what we call the Poisson equation, or basically the thing that the way the gravitational potential is created by matter. And this is something that can be tested probably in a couple of years with a Euclid satellite that was launched a year ago. So it's a very important thing. That I will skip, okay, and I will just tell you how this idea to test general relativity, and I will finish with that. The first most important things in general relativity or in gravity in general is what we call the equivalence principle. Do you know what the equivalence principle is? Who don't? Okay, you all know. Okay, so you remember maybe that the story tells that Galileo in 1630s, he was making experiments on the Pisa Tower, and he realized that, but it's not true, historically not true, but he found ways to understand that it should be the case by thought experiments, that if you take two different masses, they should fall exactly in the same way if you are in vacuum at the surface of the Earth. And then he said, okay, I'll take, we will define here, it's a number which is, I didn't define it. I take two objects, 1 and 2, and I take the relative acceleration divided by the mean acceleration. So if the two bodies fall exactly in the same way, this is eta equals 0. So Galileo, he has no way to make the experiments, but he can estimate that basically it's about 10%. Then Newton did the experiment with swings of different kind of matter, and it was done better by Bessel. Then there was torsion balance, and we measured the way, since 94, the way the moon and the earth fall in the gravitational field of the sun. Okay, they orbit, but they fall towards the sun. And so we know that basically this equivalence principle holds at 10 to the minus 15, and the latest measurement are these constraints, so 1.5 at 10 to the minus 15, and it was thanks to the microscope satellite that was launched in 2022. And this is very important because, you know, when I make this model with this scalar field interacting differently in different places of space, actually this will induce a violation of this principle. So most of these models, they are constrained from the fact that locally on the solar system scales, we should not be high effects higher than 10 to the minus 15. This is a pure killer. You will see a lot of cosmological models where you have like some kind of deviation from general relativity. You can explain galaxy, whatever you want. But if you take these models in the solar system, most of them, they will not be able to reach this thing. So it's a very important thing. Then the next thing is that we realize that it has another consequences. If this principle does not hold, it means that what we call fundamental constant are not actually constant. They should vary. They should take different values in space and time. And this is something that we can test, and we have made a lot of tests about this. I made a list of the kind of experiments that we have been performed. We can compare atomic clocks in Earth. If we do that, we compare the rate of atomic clocks, and it will put constraints on the fine structure constant, the ratio mu between the mass of the electron and mass of the proton, and the GI, which are the gyromagnetic factor of the atom. So this is pure quantum physics. In the lab, high precision atomic clocks at an accuracy of 10 to the minus 16, 17, for instance, per year. Then we can use quasar spectra. You see the light of spectra and of quasars, and you can ask whether the spectra, let's say, of the atoms you know on Earth were the same 2.5 gigayears ago. That we can compare at the level of 10 to the minus 5 today. We can use nuclear physics with the Oclo phenomena, which was a nuclear reactor that operated about 2 billion years ago in Gabon. We can use meteorites because the abundance of elements in meteorites, they will tell you about nuclear decay reactions on the time scale of 5 gigayears. And we can use cosmic microwave background and BBN. If you change the fundamental constant in a very tricky way, this is a mess of nuclear physics, but it will change the abundances of light elements and the temperature anisotropies. As I told you, about 15 years ago, when we saw that the deuterium error bars was much larger, there was a solution to the lithium problem by assuming that actually some of these parameters has changed during the history of the universe. But today, this is not the case. And if I make a summary of where we stand today, and I will stop here, yes. We get, so this is basically the level of constraint we get on these different systems. So today, on Earth, there is no sign of a variation of any fundamental constant at the level of 10 to the minus 17 per year. Okay, so this is high accuracy physics. And if you go back to the age of the universe, the relative variation is 10 to the minus 5 for quasars, and 10 to the minus 2, now we are 10 to the minus 3, I would say, for CMB and BBN. So we have a slight window to have this modification of gravity, but it's very slight, because the more we have data, the more it's difficult to get models that will fit with such a huge set of constraints. And yes, and to finish, I'll just do some kind of... Do you remember that we always said that in 1919, Eddington observed the deflection of the light by the sun, and it was a test of general relativity? This is what is written in all books. It's correct. But the question is, why is it a test? Why is it a test? And actually, if you think about what happened, is the following. Is that what happened with Eddington is that he was able to measure the deflection of the bending of light of stars that were going near the sun. So you have to wait for an eclipse to see that. So basically, you have two stars on the top during the eclipse, and after the eclipse, and you can see the measure the bending of light. But the bending of light is given by general relativity, and it depends on the mass of the sun. Okay, all the other quantities are known, the gravitational constant, and this is the distance of the ray from the sun and the speed of light. So if you don't know the mass of the sun, this is not a test. This is a way to measure the mass of the sun. Okay. The chance that Eddington had is that before him there was Kepler and all the astronomers who knew about the law, the Kepler law, the third law, of the motion of bodies in orbits. And from the motion of all Mercury, Venus, all the planets, you know that this law holds. And you see, you have the period, the orbital period P, and you have the semi-major axis A. These things can be measured. This is the time, this is the distance. And from these laws, actually what you do is that you measure the mass of the sun. So you realize that you have two ways to measure the mass of the sun. Either from motion, here, or from the bending of light. And actually, they do not behave in the same way. So they are consistent if your theory of gravity is correct at the level of your observations. And that you can ask yourself, so basically, you need c'est en français. Okay, it's okay. You need an agreement between these two measurements. The measurement of the mass of the sun using lensing or bending of light, and the mass of the sun using dynamics. And this is the motion of particles or planets. And if you don't have an agreement with these two measurements, it tells you that your law of gravity could not be either Newton gravity or Einstein gravity. It has to be something else. And what is nice is that it's easy to do in the solar system because you measure everything, but you can do that also in cosmology. And this is something we realized about 20 years ago, is that if you take the light of distant galaxies flowing through the universe, you have all the large-scale structure, and you see you have the matter distribution, but the light will be distorted. This is what we call weak lensing, and I think Hélène told you about weak lensing yesterday. You have weak lensing. And actually, matter distribution and velocity distribution, and I think she told about velocity distribution, there are two ways to measure the dynamical mass of this large-scale structure. And then you have the gravitational effect, the lensing effect that give you another measurement of the mass. And what is nice is that actually this is by combining the two and asking whether these two sets of observation would agree is a way to test general relativity on astrophysical scales. And this is what will be done by Euclid. And now we have a different set of observations that allow to measure masses on different scales, from redshift space distortion, the weak lensing, distribution of cluster, and so on and so on. And basically, with thanks of all these observations, and in particular Euclid, we will have a hint of how well is general relativity describing gravitation on the size of some 100 of megaparsec, which is something we don't know today. We don't have direct proof of this. So you see, I will stop my talk here. I've been too long. But what I want you to keep in mind is that, okay, we have this dark matter, this dark energy. There are many possibilities. Physics is, new physics is a way, but there are many questions we have to solve before that. I mean, is there a need to go beyond lambda? It's not clear. Do we have a clear proof of new physics? I would state that no, because we have to be sure that the correctness of the cosmological model to make all our predictions, and we are far from being sure we do that at the level of that's required by the observation. And so basically what is important is to test what I would say correctness. And you have heard, and this will be my last word, that we are today what people call era of cosmological in the era of precision. Precision is nice. It means that your error bars are shrinking and you know better and better. Precision is not correctness. And what you want to do is whether your cosmological model is correct, in the sense that it predicts what you observe with error bars and a precision which is high enough so that your observations are well interpreted within this model. And this is very difficult because precision, you just higher the number of observations, you ask yourself about systematic effects, and you will have an idea of whether you have precision. Correctness, you have to be sure that your theory is a good theory to describe all your observations. And this afternoon, you will be at the Bureau International des Poids et Mesures. And in metrology, this is exactly the problem. It's not having precision, it's having precision and correctness. So better and better measurements, while the physics needs to be under control at this level of observation. And this is what we call in metrology fidelity. When you have something which high fidelity, you have both precision and correctness. And this is what the goal of what we want to do in physics. We can do in lab physics because we can repeat experiments. Questions, can we do that in cosmology? And I think this is where there is still a lot of work to be done. Okay, and I stop here. Thank you.
Okay, so do we have any questions? Ah.
No, just for me, because this is the first time we have this kind of conference, and we were discussing that because we don't know, I mean, whether you are master student, undergrad student, or whatever, or high school student. What I said here, was it like too difficult, too easy, too whatever? It's very important because, you know, if this kind of conferences have to take over, it has to be fitted in you know, for all of you. And it's very important to know that. I mean, is that what I said? There are a lot of things that you knew before, or it was like way too difficult. Just, it will be an interesting feedback to have.
Thanks. No, I just wanted to say that I thought it was actually really great because it's not that narrow that it only fits master students or so. This is like applicable and usable for everyone, and not like just high level. You still delve into very interesting topics. So I really appreciate it, being a master student myself.
High school students? Okay. The others, you are just astronomers, amateur astronomers? No? Vas-y, tu peux. So mostly it's, you are high school, undergrad, and master students. So it's a quite large span of levels. So this is a difficulty. But so it's important to, if you can, not now, but give a feedback to Alexandre and Merlin about the different talks you got during the 3 days to see which one were too difficult, or so that next time we can, you know, ask the speaker to tune to a certain level so that it's be more useful. So it's a bit experimental this year on that. Otherwise, you don't have questions? No, you have understood everything. So I was too easy. So now you want more questions?